Richard Tomasetti with Thornton Tomasetti in New York. I'm glad we're only principally focusing on one project here because your company has done so much that it would be very hard to, or very easy to have a 2-hour conversation and not even touch on everything that Thornton Tomasetti has done.
Thank you.
Technical twisting and turning in the Chicago Spire. We're all hoping this gets built, and we're all getting perhaps a little more familiar than we want to with the foundation system out there, but what can you tell us about what your firm is doing with the design of the Chicago Spire?
Well, we've been very active as the engineer of record for the structural engineering, working with Shelbourne Properties and Santiago Calatrava, who's the architect and the engineer, and with the architect of record, Perkins and Will. So at this point, most of our design work is completed, and we're waiting for the project to go forward. And much of it has gone forward already. There's an entire foundation system that's in place, including caissons and the perimeter walls and a cofferdam in the center of the site, and the caissons that support the core. So it's really in a ready-to-go position right now.
While this project is on hold and hopefully to resume, you have a 100-foot deep, I won't say hole in the ground, but something where the building should be. What's being done to maintain that during this time?
Well, the site's being maintained in the same way it would be maintained during a normal construction, okay, while you're waiting to get your superstructure materials, whatever dewatering is necessary, security. So the site is being maintained in that respect. But I would not classify it as a hole in the ground. It's more a major foundation in the ground that's ready to accept a superstructure on it. So
I know that's a rather inelegant name. We were at the John Hancock Center yesterday and heard a story from the building's chief engineer about them punching a hole in the floor in the bottom floor, doing some work and accidentally going through the membrane and having really a gusher of water come up through there about to the ceiling. And I'm wondering what kind of water issues that you're dealing with at the Chicago Spire site, because it's right there on the Chicago River and next to the lake.
Yeah, actually, absolutely nothing unusual at all. We have tons of buildings in this city that are being built right next to the lake or right next to the Chicago river, where you have high water tables, and the normal conventional dewatering processes that are very common here in Chicago are being employed to prevent any problems.
Is it fair to say that whatever you're doing out there now is really going to have to be done throughout the life of the building anyway?
No, because once you finish the foundations, okay, once you totally enclose the site and the structure has been completed, you go into a different phase. There may have to be sometimes some dewatering. But keep in mind that this site is totally contained with this slurry wall and as well as a drill pile wall as part of the perimeter wall, which of itself is physically keeping out the water from the site. So the dewatering is not a major issue.
When they hopefully resume construction out there, the entire foundation system is in place, so where can they pick it up? What's going to be task one when they resume?
Task one, when they resume, will be essentially building the superstructure on the caissons that are in place and doing the top-down construction, which builds the superstructure for the lower levels, okay, below the grade, at the same time as we're building the superstructure above that, which saves you much time and money in your schedule.
Describe the top-down construction for me a little bit more. Is that you're working on ground level basically, but you're constructing underground?
Yes. Well, top-down construction, which has been used in many projects throughout the world, probably more overseas than used in the United States. And essentially, it's a process of pouring your first slab, first floor of your lower levels first, okay, without doing any excavation. All right? Using the soil below as your form for that slab, and leaving some holes, right? And then keeping in mind that you already have all of your caissons in, okay? And so you basically have your, quote, columns to hold up that floor. Through some holes, you start digging out the soil underneath that first slab until you create a space underneath, okay? And then you flatten that out, and you pour underneath the ground floor slab, you pour your first basement slab. Okay? And by doing this, as you're going down, you're automatically providing the horizontal resistance to the perimeter wall in a very stiff way to minimize any deformations and deflections in the surrounding areas. And it also provides you to have the perimeter wall in without using any exterior supports temporarily to hold that perimeter wall. Keep in mind, we have water on two sides of this, and we have the highway area on one side, and we've got condos on the other side, so there's really no way to have tiebacks for the walls or anything that goes out of the site. This is a very efficient way of maintaining the ground around the site, minimizing deflections, and doing a construction downward while you're also going upward at the same time.
Tell me about Santiago Calatrava and your relationship with him here in Chicago. Of course, we know him from the Millennium Park Bridge and the Milwaukee Art Museum. Have you done projects with him before? We've
worked with Santiago Calatrava on a wonderful project that was designed in New York, 80 South Street. Beautiful project with a variety of cubes, okay? That has been almost essentially designed, okay? But again, like in our economy these days, that's also a project that is not going ahead at this time. And we work with Santiago and Calatrava in a fascinating way because he is the architect and the engineer on the project. And he has a very capable structural engineering group that assists him on many of his projects. And then we are providing the engineer of record services and bringing in our experience of implementing a very, very high-rise type of structure with all of its challenges. And those challenges also being, how do we do something like that in an economical way right here in Chicago?
Let's talk specifically about the design of this thing. It seems like everyone, the turning torso buildings are, you're seeing a lot of them these days. And how is this similar to the ones that are out there now, and how is it different?
Mm-hmm. There are two ways of doing this, okay? The motivation from a technical point of view for these twisting and turning type of designs is that it breaks up the vortex shading around the building from the wind loads, which causes a lot of crosswind accelerations, which affect the comfort that you would feel as you get near the top of the building. So it's an interesting integration of the real design part of architecture and the engineering to collaborate in a way on what the shape of the building should also be to minimize the both the accelerations and the wind loads on the building. And there's a variety of ways of doing this, okay? Some are done where the structure tends to truly follow the form of the building, which is the type of thing I believe we're doing here with the Santiago Calatrava's Spire, because we have a very straightforward structure. We have these circular outriggers that go out and then grab the outside columns, And the main structure, although it's not exposed, it's kind of expressed in a way that you actually see it coming down at the very bottom when it splays when it splays out. Okay, it can be different than other structures because another approach to these twisting and turning type of buildings is to build a kind of a structural core, okay, that then reaches out and grabs some major columns on the outside, okay, and then allow the architecture to sway in and out and twist in and out between these major elements. So that's another way of doing it. But the basic concept that the geometry is helping reduce the wind forces and accelerations, okay, is common to all of these type of turning and twisting buildings.
Is the structural engineering, the outriggers on this project, there are how many around the perimeter of the building?
There's 4 levels of outriggers.
Okay, and I know that on some structures, the structural engineering is kind of expressed in the design of the building. Does this, is this really happen here, or is that kind of covered up by the building's form?
I would say it's covered up by the form. It's not an exposed structure. But where the two come together is that on this building, the architecture is circular as far as the floor plates go, and then the outriggers are circular. And what we were able to accomplish with these unique circular outriggers was to have these outriggers reaching out to the core, but no structure from the outrigger going through the core. So you have to think of it as a core, which is a sleeve, and then you put a circular outrigger around it and kind of make it tight to that. And as the core moves, the outrigger moves. And it grabs all the columns all the time. So you have all the columns always working for any direction of wind force. So in that sense, there's an expression of the structure, or a non-expression of the structure by providing greater space for mechanical areas and other areas that is of interest to the architect and the owner.
I want to talk about some of the design points of the building, but before I do, this project has been around in one form or another for quite some time, because it didn't start out as being a 2,000-foot tall building. It started out as about 1,500 feet with spires or structures on top of it, and then antennas, or I don't remember the entire exact history, but how much of this have you been around for?
Oh, we were involved with Santiago Calatrava at the very beginning of this. Okay? And that was another pleasurable thing, that we have this interface with him and with his structural engineering group from the very beginning.
From the Fordham Spire days?
Yes.
Correct.
Right after the Fordham Spire days. Okay?
Was Fordham out of the picture, or were you working with them on their designs?
I'm trying to recall, but I think during the Fordham Spire days, I'm not that familiar with that. I think there was a certain level of engineering had been done at that point, and then when they decided to go to the next step, that's when we got involved. But, and that's when we really collectively, working together with their structural engineering department, decided on what the structural system should be. And it was like every other project. We started out with 2, 3, 4 different types of concepts for utilizing the structure, studying them, and then finally optimizing a final solution.
And there were what, 3 or 4 versions, I think, that you had in your PowerPoint of three
essentially.
3 versions. So there were 3 major versions of the structure that you worked through.
Yes, and those 3 represent major design points, okay, and major points of seeing what would best work in the wind tunnel. Obviously, in the design process, there were other considerations in between. There was a lot of very subtle twisting and turning, so to speak, to get just the exact right form that was that best met Santiago Calatrava's architectural requirements, and also worked efficiently from a technical point of view in minimizing accelerations and forces due to wind.
Some of the technical points here, of course, every building, every big structure pretty much undergoes wind testing, wind tunnel testing anymore. Did this design display any kind of unique properties in the wind tunnel that maybe you hadn't seen before?
Yes, there were unique properties, okay, in that this is a slender building, which is all part of the beauty of the building, in my opinion, and has a high period. And normally, when you look at the dynamics of a building relative to its sway, you have different mode shapes, okay? And it's like different frequencies, okay? You can vibrate something at different frequencies. And in your typical building, you're just dealing with one mode shape. Okay? In this building, the higher order mode shapes, when the building might do a twist like that, these are infinitesimal things that are happening with vibrations. You're not seeing any of this. Okay? Those higher order mode shapes were contributing to the dynamics of the building. Okay? So that made the wind studies a lot more interesting, let's say, and a lot more challenging than a typical 60 or 70 story building. The other thing that was interesting and very significant, that with the high period we had in this building, which was about 18 seconds, meaning that it takes 18 seconds for the building to go back and forth when it's moving at its natural frequency. With that kind of high period, we had no acceleration problems on the top of the building that affects comfort based on the normal standards that we use for the maximum wind expected in 10 years. We call that the 10-year return, which is the normal criteria for comfort. But we had accelerations at low wind speeds, which were lower accelerations than at the higher wind speeds. But the lower wind speeds come more often. You would see them every year. You would see it every month. Those accelerations, working with our WDI, our wind consultant, were considered to be a little too high for the lower wind speeds. So the very unique thing about this building is we wound up designing mass dampers to be put in the building to make the building more comfortable at the lower wind speeds. It wasn't really necessary for the higher wind speeds.
Interesting.
And what made it even more interesting, because there was a sense from a lot of people, and is this really a problem? Okay? And we did this simulation that's shown in the slides, okay, in Newfoundland, where it's a ship simulator which simulates the motions of the building, okay, and then activates electronically the mass damper, so you could actually feel as an owner what these different levels of acceleration feel like.
Did they do this when they showed the building?
I'm sorry?
Was this something available to prospective tenants who wanted to buy in the building?
No.
Okay.
No, okay. They could, you know, it's a big thing to set this up.
Sure.
Okay? You can't have people just going in all the time. This is a major technical thing. Okay. And that wouldn't be necessary because it's all part of the technical analysis to make sure you get this to the point where you can
don't feel
say
it.
that you're not having the problem. Okay. So it's the first time this type of motion simulation testing was done, comparing how the building feels with the accelerations, and then how it feels when you minimize those accelerations due to activating the mass damper. Now keep in mind, the accelerations on this building were low. At the high wind speeds, you don't need a mass damper. It was doing fine. But it was felt by the owner, based on all this experimentation and the development that we did, that there were certain accelerations that were happening once a month or once a year that someone might start feeling that perception, okay, getting that perception. And therefore, we utilize the mass dampers to get rid of that.
We've seen tuned mass dampers in buildings, and when people think of them, I know when I think of them, I think it's just one big mass at the top of the building, and that's what we've seen. And this one has a compound pendulum, a compound damper system to detune the building with modes of operation.
Well, the compound pendulum is one method of doing a tuned mass damper, and that's not what we actually have. It's one of the ones we studied. Okay? And all that basically is, instead of having one mass that goes back and forth on the pendulum, you hang more than one mass in a kind of geometry, so it moves back and forth together like this, and you save space in the building by doing this. But whether it's a compound pendulum or a regular pendulum, the tuned mass damper is a passive damper. You tune it to the frequency of the building, okay, and then it kind of moves in the opposite direction when the building is swaying. The issue about the tuned mass damper, it can only dampen one frequency at a time, which is normally fine, and it's usually the fundamental mode of the building where it just moves back and forth as a cantilever. On this building, because the secondary modes, as I mentioned before, okay, were contributing to the accelerations, you would have to have more than one tuned mass damper. One set for one period, another set for another period, right? So it made sense to go to an AMD, an activated mass damper, which senses what's happening in the building. And instead of being passive, okay, through an interesting control system, it gets activated in a way to respond to more than one frequency of vibration or more than one mode shape period. It's the same thing. And by doing that, you wind up having just one tuned mass damper in one spot and maximize the space in the building for the owner.
If we've covered all of the Chicago Spire that you want, I've got a couple other questions just about general things. As a structural engineer, I know that you wanted to speak about how the structural engineers and the architects are really working more closely together now than ever before. I mean, it used to be your job to kind of give life to whatever form was drawn, and now the technology is such to where you really have to work together a lot more closely.
I think the process of working together closely in many areas has probably been going on for a long time with major architects and major buildings and projects. But because we're doing more and more major buildings and more major projects, we're seeing more of this type of collaboration. And I think it's very important that the engineering be considered at the very, very beginning, because the engineering should make a contribution to the building. The approach should be the building solution, not the structural solution. What's the building solution? And that's a combination of how you integrate the architecture, structural engineering, MEP, sustainability issues, and many other things that get involved with the building. So, for example, you shouldn't be just striving for the structural system that makes the makes itself a self-serving entity, and you can say, we have the lightest structural system or the cheapest structural system, okay? You should be striving for a structural system that makes the whole building most cost-effective, okay? That makes the whole building maximize the space for the owner and the tenant. So it's more working closely with the architect in the beginning, and even sometimes challenging the architecture, okay? And with really good, confident architects, okay, they enjoy the challenge when the engineer, MEP, or structural make suggestions that can improve the building that may require a challenge to the architect as to what he's doing with his architecture. And out of that process comes what I believe is a very good collaboration that gives you the building solution that really fits the architect's vision and the owner's vision.
What do you, as a structural engineer, you have to stay on top of what's going on in the industry, and now we're seeing building proposals that are 1 kilometer tall. We're seeing buildings of a size, proposals of a size, and serious ones of things that we wouldn't even have dreamed of, except in maybe science fiction 30 or 40 years ago. I don't know that you're getting to work on one of these yet, but what do you have to do to keep on top of what's going on in your field, that if the phone rings one day and you land one of these jobs, that you're able to address that?
Well, we have been involved on more than one occasion in kilometer-high buildings or mile-high buildings, either, which are even higher. So we've done studies on these buildings in a couple of instances. Most of these are very secret projects.
And they've been out there for a while.
Yeah, yeah. Okay, but there's some that are out there that we don't even know about or won't talk about. But what we do have to do is, from a structural engineering point of view, is stay on top of what really is necessary to make these feasible from a structural engineering point of view. Now, let me give you an example. When you get that high, the strength and stiffness of the materials you're using becomes extremely important. For example, with a mile-high building, if you use 10, 11,000 PSI concrete, okay, which is like roughly 80 or so, 90 or so MPa in the metric system, okay, the mile-high concrete column will be at its allowable stresses at the bottom, just from the weight of that column. So you can't add anything else to it. You can't use it for anything else. You can't support a floor. You can't use it to help resist the wind loads. So that lets you know that you've got to have very high strength concretes to make these buildings efficient, right? And so it's that type of thing you have to stay on top of. But I think also the feasibility of these buildings also lies in a lot of other areas that may be even a lot more important than the structure. We'll get it up there if we have to. We know we can do it, okay? But the sociological implications, the infrastructure implications, things of that nature, the elevatoring for these buildings are something that really has to be studied in conjunction with all the disciplines. How do the elevators work when you have the amount of movement that you're getting in a building that's a kilometer high? A lot of interface has to be there. So the elevator people have to be on top of how structures are behaving, and the structural engineer has to understand how the elevators behave, more so than ever before compared to a 50 or 60-story building.
Well, and it's not just a question of throwing up mass, because those extreme stresses at the bottom that you mentioned, Do we have the materials right now, or are those materials under development that will sustain those kind of loads?
No, I think we have those materials because, like, for example, even on the Spire, we were using 110 MPa concrete. That's more than 16,000 PSI concrete. So I think we have those materials. But you have to have those materials and the capability of bringing those materials to the particular site that you're considering for these extremely tall buildings.
Well, I want to thank you for coming by to discuss the Chicago Spire, and all of us in Chicago are hoping to see that building. We've been looking for a 2,000-footer in this town now since Caesar Pelli, well, even before that, and there have been so many that have gone by the wayside that we hope this one gets built.
Yeah, Chicago has a very interesting history of searching for the 2,000-foot,
The elusive 2,000-footer.
foot building, and hopefully we will get there as our economy comes back with this one.
Richard Tomasetti, thank you so much for coming by.
Thank you,
Good
Jeff.
to see you.
It was a pleasure. Thank you.